The name black hole is already misleading. It makes you imagine a hole in space, a dark tunnel, a cosmic drain where matter falls and disappears somewhere else. But physics never actually predicts a hole. There is no opening in the universe, no edge you collide with, no interior cavern waiting on the other side. In fact, if you fell toward one, the strangest thing would happen. The moment you crossed its boundary, absolutely nothing special would occur. No flash, no jolt, no sensation of crossing anything at all. Yet to someone far away, you would never fall in. You would freeze forever at the edge, your last moment stretched across eternity. So did you enter or not? A black hole is not an object sitting in space. It is a place where space and time exchange roles, where forward motion points inward, and where later becomes a direction you cannot avoid. You don't fall into a black hole the way you fall into a pit. You fall the same way you move into tomorrow. And once you understand that, the word hole stops making sense. Before we can understand a black hole, we have to fix the first lie physics ever told us. Gravity does not pull things. It feels like it does. When you stand on the ground, your feet press downward. When you lift a bag, your arm strains. When you jump, you come back to Earth. Every sensation tells you something invisible drags you toward the planet. But the truth is, stranger, right now, at this very moment, you are not being pulled down. You are being stopped from falling. The falling person feels nothing. Imagine stepping off a roof, not the fear, just the physics. For the first instant, your body becomes weightless. Your stomach rises. Your muscles relax. The pressure in your feet vanishes. That feeling is not gravity turning off. It is gravity finally acting alone. A freely falling body feels no force. Astronauts orbiting Earth float for the same reason. They are not far from gravity. They are constantly falling through it. The spacecraft and the astronaut follow the same path through space-time, so nothing presses on them. Weight appears only when something interrupts that motion. The ground prevents you from falling. The floor pushes up. Your bones compress. You interpret that resistance as gravity pulling you down, but it is actually the Earth preventing your natural path. Weight is the sensation of being stopped. Straight paths in a curved world. Newton imagined gravity as attraction between masses. The mathematics works beautifully, but Einstein asked a deeper question: what if motion under gravity is actually natural motion? Picture an airplane flying straight across Earth without turning. The pilot holds the wheel steady, yet the plane traces a curved path around the planet. From space, the route curves. Inside the cockpit, it feels straight. The surface beneath the plane is curved, so the straightest path available bends. Einstein proposed the same idea for the universe itself. Mass bends space-time. Objects simply move straight within that bent geometry. The apple does not curve toward Earth because Earth pulls it. It follows the straightest possible line available in curved space-time. Falling is not caused by force. Falling is the absence of force. Toward extreme curvature, now imagine increasing that curvature. Near a planet, straight paths gently converge. Near a star, they bend more strongly. What if curvature becomes so extreme that every straight path leads inward? Not because something grabs you, because outward directions no longer exist. That is the beginning of a black hole. The river that becomes time. Think of a river flowing toward a waterfall. Far upstream, fish swim freely in any direction. Closer to the edge, the current strengthens. Eventually, the water flows faster than any fish can swim. At that point, every effort, even swimming away, still carries the fish toward the fall. The waterfall does not pull the fish. The river defines all possible motion. A black hole is space-time behaving like that river. A black hole is not a place where gravity becomes infinitely strong. It is a place where forward motion itself points inward. You do not fall because something drags you. You fall because every possible future path leads there. And that means from the very beginning, the name is wrong. It was never a hole. Once you accept that gravity is geometry, the next mystery appears. Where does a black hole actually begin? Surely there must be an edge, a surface, some kind of dark sphere floating in space, marking the point of no return. But the most important boundary in a black hole is not a surface at all. You cannot touch it. You cannot see it directly. And when you cross it, you won't notice. This boundary is called the event horizon. Not a wall, but a rule. The event horizon is defined in a strange way. It is the place beyond which signals can never reach the outside universe. Nothing physical blocks the escape. Light doesn't bounce off it. You don't crash into it. Instead, the structure of space-time changes so that every possible forward path leads deeper inward. Imagine standing on a mountain slope so steep that every direction you walk leads downhill. Even if you try to go sideways or backward, gravity carries you lower. The horizon works like that, but with time included, crossing quietly. Picture falling toward a gigantic black hole millions of times heavier than the Sunday. Because it is so large, tidal forces at the boundary can be gentle. You drift closer. Your heartbeat stays calm. Your watch ticks normally. Then you cross the horizon. Nothing happens. No flash of light. No sudden pull. No moment you could mark and say, I just entered. Locally, the laws of physics remain ordinary. You continue floating as if nothing changed. But something has changed, only not in a way you can feel yet. The outside perspective. Now imagine someone watching from far away. As you approach the horizon, the light you send out stretches to longer wavelengths. Each signal takes longer to reach them. Your motion appears slower and slower. You fade. To them, you never quite reach the boundary. You freeze at the edge of darkness. Your final moment stretched across eternity. From your point of view, you crossed in seconds. From theirs, you never cross at all. Both descriptions are correct. What the horizon really is, the event horizon is not a place in space. It is a limit in cause and effect. Outside it, events you cause can still influence the universe. Inside it, they never can again. No material barrier is required. Geometry alone separates the possible futures from the impossible ones. A black hole does not trap you with a wall. It traps you because away stops being a direction the future allows. You pass the horizon without noticing, yet from that moment onward, every tomorrow leads deeper inward, and still, you feel nothing. By now, the black hole already refuses to match imagination. No pulling force, no solid edge, no dramatic crossing. But the next idea is the one that truly breaks intuition. Inside a black hole, the center is not somewhere you go. It is something that happens to you, space and time in everyday life. Right now, you have freedom in space. You can walk forward or backward. You can turn left or right. You can stand still if you choose. But time offers no such freedom. You cannot stay in this second forever. You cannot return to yesterday. You cannot pause the next moment from arriving. Time always moves forward. In ordinary life, space optional, time unavoidable. The role reversal. Inside a black hole, space-time bends so strongly that these roles exchange. The direction toward the center becomes time-like. That means reaching the singularity is as inevitable as reaching tomorrow. You do not have to move inward. Your future is inward. Trying to escape would be like trying to stop time. No engine, no rocket, no imaginable force can prevent it, because you are not choosing a path in space anymore. You are following the only path time allows. Even light cannot escape. Light always travels the fastest possible route through space-time. Yet inside the horizon, every allowed route points deeper toward the center. Not because gravity pulls light, because outward paths no longer belong to the future. To leave would require moving backward in time relative to the geometry, something nature does not permit. All tomorrows point inward. The singularity is not a location. People imagine the singularity as a point waiting at the bottom of a tunnel. But inside the horizon, it behaves more like an event waiting ahead. You don't aim for it. You age toward it. Distance becomes duration. Just as you cannot avoid next year, you cannot avoid the center. A black hole is not a place where gravity wins. It is a place where direction changes, meaning outside, you choose where to move in space. Inside, you cannot choose not to reach the center. You don't fall into a location. You fall into a moment that lies ahead in time. From the traveler's perspective, crossing the horizon was quiet and uneventful. No flash, no impact, just continuing forward toward an unavoidable future. But to the rest of the universe, something astonishing happens. The fall never finishes. Watching a star become a black hole. Imagine a massive star exhausting its fuel. Without pressure pushing outward, gravity makes the core collapse inward. From nearby, the collapse completes quickly. The star shrinks past the horizon and continues inward. But from very far away, the picture looks completely different. As the surface approaches the horizon, the light escaping from it takes longer and longer to reach distant observers. Each wave stretches to lower energy. Each second appears longer than the last. The star slows, then slows more, then almost stops, frozen at the edge. To distant observers, the surface never quite crosses the horizon. It approaches endlessly dimmer, redder, weaker, but never disappears. Instead of seeing the star fall inside, they see it fade into darkness. What we call a black hole is really the final visible image of matter eternally nearing the boundary. The universe never literally watches anything go in. Two valid stories. So what really happened? Did the star collapse completely? Or is it still hovering at the edge? Relativity gives a surprising answer. Both descriptions are correct. Time does not pass identically for all observers. The horizon separates regions that cannot agree on the order of events. From one viewpoint, the collapse finishes. From another, it never does. A boundary of time. The horizon is not just a spatial boundary, it is a boundary of storytelling. Inside, events continue normally. Outside, the last moment stretches forever. Neither observer is wrong. Reality allows multiple, consistent histories depending on perspective. A black hole is not merely a place where matter disappears. It is a place where observers cannot share the same timeline. For one observer, the fall completes. For another, it never finishes. The black hole becomes less like an object and more like a division in reality itself. For a long time, physicists believed black holes were the ultimate endings. Once something entered, it was gone forever. No escape, no return, perfect darkness. But when quantum physics met gravity, the universe refused that conclusion. Black holes are not completely black. They glow. The activity of empty space, quantum theory says empty space is never truly empty. Even in perfect vacuum, tiny particle-antiparticle pairs constantly appear and vanish. They flicker into existence and annihilate before they can be observed. Normally, this activity cancels out perfectly. But near the event horizon, space-time curvature interferes with that balance. A pair divided. Imagine a pair forming exactly at the horizon. One particle falls inward, the other escapes outward. They can no longer meet to annihilate. To a distant observer, it looks as if the black hole emitted a particle. This is Hawking radiation. Nothing tunnels out of the hole. Instead, the structure of space-time allows part of the quantum fluctuation to survive. The black hole shrinks. The escaping particle carries energy away. Energy equals mass. So the black hole loses mass. Extremely slowly for large black holes. But inevitably, over unimaginable time, it evaporates completely. The ultimate prison has an expiration date. A thermodynamic object, even stranger, black holes have temperature and entropy. They obey the same thermodynamic laws as ordinary matter. The horizon behaves like a physical system containing microscopic states. A black hole is less like a bottomless pit and more like a hot coal radiating heat. Black holes cannot perfectly trap reality. Quantum mechanics forbids absolute stillness. So the darkest objects in the universe slowly shine and eventually vanish. They are not eternal voids. They are temporary processes written into space-time. By now, the black hole has lost every familiar meaning. It is not a tunnel, not a solid object, not a permanent prison. So what actually waits at the center? According to Einstein's equations, space-time curvature keeps increasing as you move inward until it becomes infinite. This prediction is called the singularity. But in physics, infinity is not a real thing you can point at. It is a warning, the end of the map. Imagine drawing a map of the world and reaching the edge of the paper. The land does not end there, the map does. The singularity is like that. It marks the boundary where our current theory stops describing nature properly. General relativity predicts its existence, but cannot explain what happens there. Something deeper must replace it. Two theories collide. Physics has two great frameworks. Relativity, describing gravity and space-time. Quantum mechanics, describing the microscopic world. Inside a black hole, both become equally important and they contradict each other. Space-time may become grainy. Time may lose its continuous meaning. Location itself may stop behaving normally. We do not yet know the final theory that unites them. The information puzzle, another mystery appears. If everything falling in is destroyed at the singularity, information disappears. But quantum mechanics forbids true information loss. So the universe must preserve it somehow, perhaps encoded on the horizon itself rather than stored inside. This suggests the interior might not be an ordinary region of space at all. The center of a black hole is not a place we understand. It is the meeting point of incomplete theories. The black hole teaches us that space-time, matter, and information are deeper than our current ideas allow. Not a final answer, but a doorway to new physics. We began with a simple image, a dark pit in space, swallowing everything forever. Now that image is gone. No surface to collide with, no force dragging you inward, no hidden cavern waiting inside, no eternal prison keeping things forever. So why did we ever call it a black hole? Because human intuition needs objects. We imagine space as an empty container and gravity as something acting inside it. But a black hole teaches the opposite lesson. Space is not the stage. Space is part of the story, a boundary, not an object. A black hole is not something located somewhere. It is a boundary in cause and effect. Outside the horizon, events can still influence the rest of the universe. Inside, every future event leads deeper inward and never returns. Nothing blocks escape. Geometry itself removes the possibility. The whole is not emptiness, it is a direction you cannot leave. The universe remembers. Modern physics suggests something even stranger. The information describing everything that fell in may remain encoded on the horizon itself, spread across its surface like a cosmic memory. Not stored in a volume, but written on an area. This hints that space might behave like a projection, where a three-dimensional region is described by data on a two-dimensional boundary. The black hole stops being a place. It becomes a relationship